Okay, so here we are, our next chapter, chapter 9. And in chapter 9, we are going to be dealing with a new number system. All right, we'll actually be dealing with what we call the irrational number system. Now, of course, as we work with a new system, you'll have to learn how to basically, once again, perform the basic operations of add, subtract, multiply, and divide. We'll learn how to simplify working with this irrational number system. Now, let me just give you some examples of irrational numbers and what makes them irrational. For example, you may be familiar with the number pi. The number pi is considered irrational because it is approximately 3.14. Okay, of course, there are many decimals that go on after that. There's another irrational number that we're going to learn a great deal about later on in chapter 11, and that is the irrational number e. Okay, e is another irrational number. It has a decimal approximation of approximately 2.718. Okay, and these decimals keep on going. They never end, nor do they ever repeat, and that's why they are considered irrational. Rational numbers, okay, for example, 1/3, 1/2, the number 4, these are all considered rational numbers. For example, the number 4 we can write as the fraction 4 over 1. We can also write it as the decimal 4.0. Okay. The 1/2 is considered a rational because it goes 0.5 and then it stops. All right, that's the decimal equivalent. 1/3 is considered a rational number because it is 0.333 repeating. All right, so these three numbers are considered rational because they either end or they repeat, whereas numbers that never end nor do they ever repeat, they are considered irrational numbers. Now, the ones that we are going to be dealing with the most in chapter 9 are numbers like, let's say, the square root of 2, or let's say the square root of, let's say, the number 3. And these are radical numbers, okay? And that's what we're going to be dealing with exclusively throughout chapter 9, okay? These radical numbers. And particularly, these are what we call square roots. The square root of 2 has a decimal approximation of 1.414, okay? And it keeps on going. And it doesn't repeat. You might think it repeats, but if we were to actually, if I was to use a calculator, let's say, and take the square root of 2, it would give me 1.414213562. Okay, let me just write that. 213562. Okay, it doesn't repeat, nor does it end. It keeps on going. If we were to take the square root of 3 using a calculator, it would have a decimal approximation of 1.732050808, and once again it would keep on going and it would never repeat. Okay, it might look like it repeats here, but in actuality it does not. It just keeps on going. And that's why these radical numbers that we're going to be dealing with throughout chapter 9 fall under this irrational number system. Okay? Now, there are going to be all different types of radicals that you are going to encounter. All right? And the basic format of your radical numbers is going to look something like this. You're going to have this funny looking symbol, that's the radical symbol. You're going to have a quantity underneath that radical symbol, and there is going to be a little number that's raised slightly in front of the radical symbol. Now, that little number is called the root index. Okay? It's the type of radical that you are dealing with. And if I was to look at the examples that we had up here, I said that this was the square root of 2. And I said that this was the square root of 3. And you might be wondering, well, gee, I don't see a little root index number. And that is because of all the radicals, the square root is the most common. And that's why there's an understood 2. Okay, you don't have to put that little 2 there, that root index of 2, because it's understood if we don't see it. All right. In math, there are a lot of things that we assume to be there. Like when we talk about x, that really means 1x. If you don't see a little number here, okay, it's assumed that we are talking about the square root. Okay, that is your root index. Now, the b value also has a name. It is often referred to as the radicand. Okay, so just be familiar with the terminology as we will use it throughout the lesson. You may see it in the book as well. All right, so the quantity that's underneath that square root symbol is called the radicand. The little number that you may see above the root index, the radical sign, is the number that we call the root index. So if we were to talk about, let's say, the square root of 4, okay, this means the square root of 4. And the square root of 4 actually has a numerical value of 2, okay? Now, how are we getting that? What is it that the square root is figuring out? Well, let's look at a few other examples and let's see if we can come up with a conclusion. Well, the square root of 9, that's equivalent to 3. The square root of, let's say, 36 is equal to 6. The square root of 64 is the number 8. And these are things that you can actually get from your scientific calculators. Most of your scientific calculators already have a square root button on it. So you would just have to activate that button and type the radicand underneath. And when you hit the equal sign, you get the answer of whether it be 3, 6, or 8. So by, let's say, taking the square root of maybe the number 100, and that, of course, would give us the number 10. Now, what is it that we are figuring out? How are we getting the 3, the 6, the 8, and the 10? What is it exactly that your calculator is figuring out? The calculator is figuring out the number that you would have to square in order to get the radicand. That's what the calculator is figuring out. So what number would I have to square to get 9? Of course, the answer is 3, because 3 to the second power, 3 squared is 9. What would I have to square to get the radicand 36? I'd have to square a 6, okay? So if I was to take, let's say, the square root of 25, I need to think of what number would I have to square in order to get 25, and of course the answer would be 5, okay? Why are we saying what would we have to square? Because we are dealing with a square root. If we had, let's say, the square root of a negative 25. Now, once again, we are asking ourselves, what would we have to square to get a negative 25? And a lot of times the common wrong answer is people put down negative 5. But if you think about it, if you take a negative 5 and square it, do you get a negative 25? And the answer would be no, you do not. Okay? Negative 5 squared actually gives you a positive 25. So this is the incorrect answer. The square root of a negative 25 is not a negative 5. However, the square root of a negative 25, if you were to try that on your scientific calculator, it may give you some type of error message. It may be so sophisticated as to say domain error. Because what it's trying to tell you is that there's actually no real number. Okay? That would be the correct answer for this point in time when we try to take the square root of a negative radicand. Okay? So what we'll be able to say here is that your radicand must be a positive number when we are dealing with a square root. Okay? So if I tried, let's say, the square root of maybe a negative 36, or if I tried taking the square root of a negative 49, or if I tried taking the square root of a negative 121, these would all have the same answer of no real number. Later on at the end of chapter 9, you'll learn about the imaginary unit, and you will see that you'll be able to go further with this. That's why we use the word real when we talk about the fact that there is no real number when you try to take the square root of those negative radicands. But what if we are dealing with a different kind of radical? There are all different kinds of radicals. If we have, let's say, the cube root of the number 8, notice my terminology here. Because my root index now is the number 3, this is the cube root of the radicand 8. So what is it that you're trying to figure out? What number would you have to cube to get the radicand 8? Okay, think about that for a moment. What number could we raise to the third power that it would equal the radicand 8? And of course the answer would be the number 2. So the cube root of the number 8 is 2. What if we try taking the cube root of, let's say, the number 64? The cube root of 64, what number can I raise to the third power and get the number 64? The answer would be 4. Okay. What if we were to take the cube root of, let's say, a negative 8? Is there such a number that when I raise it to the third power, I get a negative 8? And the answer is yes. If I take negative 2 and I raise it to the third power, I will get negative 8. And that's why we can say that the cube root of a negative 8 is a negative 2. If I was to take the cube root of, let's say, the number negative 64, that would in fact equal a negative 4. Okay? So it's okay if we have a negative radicand when we have a root index that's odd, like the number 3 here. There are some other root indexes. I could have, let's say, the fourth root of the number 16. The fourth root of 16 happens to be the number 2. If I was to try to take the fourth root of a negative 16, once again we would have to say no real number. If I was to take the fifth root of, let's say, the number 32, what would I have to raise to the fifth power to get 32? The answer would be 2. If I was to take the fifth root of a negative 32, now we would get a negative 32. Oh, negative 2. My apologies. So a few observations here that we can make. Once again, let's define our radical. Once again, the radical is made up of your root index as well as your radicand. Now, if the root index is even, whether it be the square root, the fourth root, the sixth root, then the radicand must be a positive number, okay? As we demonstrated, okay? We took the fourth root of 16, we got 2. We took the square root of a whole bunch of different numbers, okay? We were able to do that as long as the radicand was positive. If, however, the root index is odd, then the radicand can be positive or negative, as we were demonstrating here. The cube root of 64, the fifth root of a negative 32, or of a positive 32. It could be positive or negative. So we want to keep that in mind as we work through our radical number system, okay? And once again, that's what we're going to be dealing exclusively throughout Chapter 9, okay? Only dealing with this radical number system. Primarily, we will deal with square roots, okay? That will be our primary focus. We may deal a little bit with cube roots, but we won't go too far beyond that. Now, when we talk about radical functions, we've been talking about functions now since Chapter 4. That's where we first introduced functions, okay? We talked about how we would, what function notation looks like. We talked about how we would evaluate a function. We even talked about the domain of a function, all right? We can also have radical functions. For example, we might have f of x equals just the square root of x. G of x, that function, might be equal to the square root of x plus 2. We could have h of x, and h of x might equal the square root of, let's say, x minus 3. Okay? Here we have 3 different radical functions. They all happen to be square root functions. How do I know that? Once again, because I don't see a root index, we are assuming it to be the number, the root index of 2. If I did, let's say, j of x, and j of x equaled maybe the cube root of x plus 3. Here we have a cube root function. Now, just like before with functions, I could ask you to do a couple of different things. I could maybe ask you to evaluate. Recall, when we evaluate a function, I have to give you the x value to substitute in, because that's your domain, that's your input. So I could ask you to evaluate, let's say, f of maybe the number 81. In which case, if I use my function f of x, I have to take the square root of 81. And the square root of 81, what number would I have to square to get 81? The answer would be the number 9. What if I asked you to evaluate, let's say, g of 7? According to the function g of x, I am taking the square root of x plus 2. So I would have to take the square root. I'm going to plug in my number 7 plus 2 more. Since 7 plus 2, that would give us now the square root of 9. And of course, the square root of 9 would be 3. We are evaluating our function where I give you the x value. I could, let's say, ask you to evaluate h of 28, which means I have to plug in the number 28 into the function h. So that would give us the square root. According to h, the rule is to take x and minus 3. So that would be 28. Let's rewrite that. 28 minus 3. When we simplify, that would give us the square root of 25. And if we take the square root of 25, we get 5 as our solution. What if we were to take, let's say, the function j of x, and let's say I want you to evaluate the function j at a negative 11. Well, we would have to now plug in the negative 11 in for x. The rule is we have to take the cube root of that negative 11 plus 3 more. That would give us the cube root of the negative 8. And by taking the cube root of negative 8, that would give us a negative 2 as our solution. That's how we evaluate a function. I must give you, once again, whenever we evaluate, you must be given the rule and you must be told what the x values are. You plug them into the rule and you simplify as much as you possibly can. Which of course is different if I was to ask you for the domain. When I ask you for the domain of a radical function, we have to be careful now. Because here we may have some restriction. Particularly when we have square roots. For example, when we have f of x equals the square root of x. That is your most fundamental radical square root function. Now here, the radicand, as we've been talking about, has to be a positive number. So in terms of the domain, what we're going to want to say is that x has to be greater than or equal to 0. 0 is the first real number that we can take the square root of, because the square root of 0 is 0. You can take the square root of any number as long as it is a positive number, and that's what we are saying about this domain. We usually represent this in interval notation, so that of course would mean that we would go with a bracket from 0 to infinity, and then we close it with a parenthesis. That would be your domain for the square root of x. Let's say g of x. Let's take a look at that function. Recall that was the square root of x plus 2. And once again, we want to know the domain of this function. Well, what concerns us, once again, is the radicand, which in this particular case is the x plus 2. So x plus 2 has to be greater than or equal to 0. This algebraic expression, the part that's underneath the radical, has to be greater than or equal to 0. And so now if we were to solve this for x, we would have to subtract the 2 over, in which case now we get x is greater than or equal to a negative 2. Negative 2 is the first number that we can plug into this function, because if I did, negative 2 plus 2 would be 0, and you can take the square root of 0. So if we were to write this in interval notation, you would go from negative 2 to infinity. All of the real numbers from negative 2 to infinity, I can plug into the function, and it would give me a mathematical answer. Let's take a look at h of x and its domain. H of x, you may recall, was the square root of x minus 3. Now, in terms of this domain, once again, what concerns us is the radicand of x minus 3. Because we are dealing with the understood root index of 2, the square root of x minus 3, we know that the domain of x minus 3 has to be, once again, greater than or equal to 0, just like we did with the other examples. By adding the 3 over, we would get the fact that x has to be greater than or equal to the number 3. Expressing it in interval notation, we would go from 3 to infinity. Let me give you one to try. Let's say f of x, we'll go back to f, equals the square root of 3 minus 2x. I want you to take a moment. I want you to work through the problem, pause the video, and find out what the domain of this function would be. Be careful here. There's a trick within this problem that you should be aware of. Let's see what you're going to do first. So pause the video and return when you are done. Well, just like in the other problems, we're trying to find the domain. We are dealing with a square root. So just like the other problems, what's going to concern us is this radicand of 3 minus 2x has to be greater than or equal to 0. This is indicating that it has to be some type of positive quantity. Now, like I said, there is a trick here. So the first thing I'm going to have to do is I'm going to subtract 3 from both sides. And of course we get negative 2x is greater than or equal to a negative 3. But since we are trying to get x alone, I will have to divide both sides by a negative 2. And now, on the left side of the inequality, we have x. On the right side of the inequality, we have 3 halves. And here comes the trick that you have to try to remember. Think back to when we learned how to solve inequalities. We had talked about that if you multiply or divide by a negative number, that we have to flip your inequality symbol. So now I have to take this inequality symbol and I have to flip it over, in which case now x is in fact less than or equal to 3 halves. So the interval notation that we would now use is a negative infinity to 3 halves with a bracket. So be careful of that. I'd be curious to know how many people forgot to flip that inequality symbol. Okay, I'm sure there's quite a few of you out there. I've been teaching this for quite some time, and there's always a few that forget to flip that inequality symbol. So be careful of that. Once again, the rule was that if you happen to multiply or divide by any negative number, you have to flip your inequality symbol. Okay? Let's just do one more. What if we had g of x equals, let's say, the cube root of x plus 7 divided by 3. Now, don't overthink this, okay? This is actually a 2-second problem. As soon as you see the fact that we are dealing with a cube root, okay, as we are dealing with here in g of x, all the other functions that we were talking about in terms of the domain were square roots. But since this happens to be a cube root, as we can see here by the root index, we don't have to think about this any further, because as we talked about, that if you have an odd root index, that this radicand can be both positive or negative, in which case, in terms of the domain, we're going to be able to say that x is all real numbers. In which case, using the interval notation, remember that is from a negative infinity to infinity. Okay? So the minute you see a odd root index, whether it be a 3, 5, 11, doesn't make a difference. As long as your root index is an odd number, that means your domain is going to be all real numbers. If you see that your root index is an even number, that's when you take the radicand and you say that it has to be greater than or equal to 0. Whether it be no number there, which means it's a square root, or it be the 4th root, or 6th root, or 12th root, since those are all even numbers, your radicand must be greater than or equal to 0. Versus if it's an odd number, your domain will be all real numbers. Okay? Now the last thing that we have to look in section 9.1, okay, is how we are going to graph square root functions. Now, when you move on to other courses, like maybe pre-calculus, you may take a look at how to graph cube root, fourth root, fifth root functions. But here, for this particular course, they only focus on the graphing of the square root radical function. And when we do that, we're going to make a table, okay? And what's nice about the table is that the majority of the table will always be the same. For example, f of x is equal to, let's just start with the basic one, square root of x. We want to see what this graph is going to be. The first thing you have to do is find the domain. What is the domain of this function? And we did that earlier. We said that x has to be greater than or equal to 0. Those are all the possible x values. And what we're going to do next is we're going to make a table. Our table is going to be made up of 3 rows, as well as 3 columns. So here we have the x. The second row is your actual function, the square root of x. And that third row, whether you write it as f of x or y, it doesn't make a difference. I'll use the variable y because they mean the same thing. Now, it's the second row and the third row that will always have the same numbers, regardless of what the function is. We're always going to put in the same numbers of 0, 1, and 4. Why those numbers? Well, because those are the first 3 real perfect square numbers. I could take the square root of 0, and we get 0. I could take the square root of 1, and we get the number 1. I could take the square root of 4, and that, of course, would give us the number 2. Okay? So these 2 rows will always be the same. It'll always be 0, 1, 4, and 0, 1, 2. Now we have to come up with the x values. They must satisfy the domain. I need a value of x that is greater than or equal to 0. So we're going to start with 0. The number is right here. That's your very first number that you're going to begin with. Because if I plug in 0 here, I will get 0. Next, I need another number, also greater than 0, that when I plug it in, I get 1. So the answer, of course, would have to be 1. So, because if I take the square root of 1, we will get 1. Now I need one more number. A number is such that I get 4. Well, x would have to be 4. So what we want to do now is, on our coordinate plane, we would want to graph these 3 ordered pairs of 0, 0, 1, 1, and 4, 2. So let me just draw a quick sketch of a coordinate plane. And we'll plot the points. We start here at 0, 0. Then I need an ordered pair, a dot at 1, 1. Then we need another dot at 4, 2. And we will connect our dots as such. Don't use a ruler here. This is not a straight line, okay? This is a curved line. Notice I don't go beyond the 0 because I can't. My x value, this has to be the very first point. Do not draw any lines in this direction, okay? That's not true. Notice this line is going to keep on growing upward, okay? Because as x gets bigger, so will y, all right? If I wanted to put more points, I would have to, let's say, put the number 9, because if I take the square root of 9, I'll get 3. Or if I plug in the number 16 and take the square root of 16, I will get 4. So as x grows rather large, y grows but in a smaller fashion, okay? So this would be the graph of your square root function, the square root of x. Let's take a look at a different one. Let's say we have f of x is going to equal the square root of, let's say, x minus 3. Once again, the first thing that we need is the domain. So I look at my radicand of x minus 3. We know it has to be greater than or equal to 0. To solve, we'd have to add the 3 over. And so x, we know, has to be greater than or equal to the number 3. That is your domain. That will help us form the graph. Next, we'll make a table. We have the x row. I'm going to have the rule, the square root of x minus 3. And then I'm going to have my third row, which is just, of course, y. Now remember, the second row will always have the same numbers of 0, 1, and 4. The third row will also always be the same of 0, 1, and 2. We have to now come up with our own x values. Remember, the x values must satisfy the domain. So what am I going to start with? Well, the answer is right here. 3 is the first number that I'm going to use. Because 3, if I plug it in, 3 minus 3 would give me 0. And when you take the square root of 0, we get 0. But now I need a number, okay? Let's come up with another number that when I subtract 3, it produces 1. Can you think of a number? Well, the number that when I subtract 3 gives me the number 1 happens to, of course, be 4. Because 4 minus 3 is 1. I need one more number. I need a number that's still greater than 3, such a number that when I subtract 3 from it, it gives me 4. What must that value of x be? But 7. So now I'm going to create another coordinate plane. Once again, I have to plot some ordered pairs and connect those dots. My ordered pairs would be at 3, 0. Then I need an ordered pair at 4, 1. Next, I need an ordered pair at 7, 2. Those 3 points are enough. I will connect my dots and form my curved line. Once again, we start here at the very first point of 3, 0. And I have to move in this direction towards the 7, 2. Okay? Let's do one more. Let's say f of x equals the square root of maybe x plus 5. Once again, the first thing that we need is the domain. Well, we know that the radicand of x plus 5 must be greater than or equal to 0. And if we subtract the 5 over, we would in fact get that x must be greater than or equal to a negative 5. That is your domain. Now that we know what the domain needs to be, once again, let's create our table. X, the first row, the square root of x plus 5 is the rule, that's our second row, and finally I use y. The second row, once again, will always be the same 3 numbers, 0, 1, and 4. And the y values will also always be the same, 0, 1, and 2. Now I need my 3x values. Well, the first one I get right here from the domain, negative 5. because if I plug in negative 5 plus 5, we get 0, and we take the square root of 0, we get 0. Now I need another number. I need another value of x such that when I add 5 to it, I get the number 1. Well, the number that you can add 5 to produce a 1 would be a negative 4, because negative 4 plus 5 is 1, and the square root of 1 is 1. Next, I need a number that when I add 5 to it, I get 4. Can you think of a number that when we add 5, we get 4? The answer would be negative 1, because negative 1 plus 5 is 4. And so, for our last graph, once again, I set up a coordinate plane. And I'm going to have to plot my points. My first point is at negative 5, 0. My second point is at negative 4, 1. And then the third point is at negative 1, 2. Once again, when we connect our dots, form a curved line. You're showing that the line continues, and that's why we draw an arrow at the end. Okay, it always goes to the right, okay, as we can see from our numbers. Okay, so that's how we graph radical equations. There's a lot more involving radicals, all right, as you will see in the upcoming lessons. Once again, we still have to learn how to simplify, add, subtract, multiply, and divide radicals. So that is to come, all right? There is homework that goes along with this section, so please give it a try and email me any questions that you may have. Until the next time, be well.